Hello everyone. Today we are going to discuss the problem road reparation from CSES graph problem set. Let's go through the problem. There are n cities and m roads between them. Unfortunately, the condition of the road is so poor that it cannot be used. Your task is to repair some of the roads so that there will be a decent route between any two cities. For each road, you know its reparation cost, and you should find a solution where the total cost is as small as possible. So first line contains two integers n and m, the number of cities and the roads. The cities are numbered 1 to n. Then there are m lines describing the roads. Each line has three integers a, b and c. There is a road between cities a and b and its reparation cost is c. And all roads are two-way roads. So every road is between two different cities and there is at most one road between any two cities according to the input. Okay. So you need to print one integer, the minimum total reparation cost. However, if there are no solutions, you need to simply print impossible. The number of nodes and rows are of the order of 10 power 5. Nodes are numbered 1 to n and reparation cost can go up till 10 power 9. So this is the input given to you. Let's try to understand what the problem is and then we will see how we will actually solve this. So over here, I just have drawn the input that is given to you. So you have basically 5 nodes numbered 1, 2, 3, 4 and 5. And these are the roads between them. So currently the condition of the roads is very poor. So I have marked them with a dotted line. And we have to repair some of these roads so that every node is reachable from every other node. So what are the two conditions we have? The two conditions, the first one of them is every node is reachable from every other node. This is the first condition that we have, and the second condition that we have is that the sum of weights, or basically the sum of cost of reparation, sum of the cost should be minimum. Or basically the total cost of reparation should be minimum. Like if you are repairing a road from 1 to 2, you are bearing the cost of 3, right? So the total cost should be minimum. So let's try to understand with the help of this particular example. So in this particular example, as I can look, if you just see, if I connect the road between, if I repair the road between node 1 and 2, between 2 and 4, between 2 and 3, and between 5 and 4. If these 4 roads are connected, you can simply see that every node is reachable from every other node because every road is a two-way road. So every node is reachable from every other node. And if you now see the sum of the cost, so the total cost basically, so it is 4 plus 2 plus 5 plus 3, which is 14. And this is the minimum that we can achieve. This is the minimum. The 14 is the minimum that we can achieve. Let's suppose we were connecting something like this. We were connecting this road, this road, this road, and this road. In this case, the total cost would have been 3 plus 7, 10 plus 2, 12 plus 5, 17, and it is greater than 14. So connecting these 4 roads or repairing these 4 roads is the minimum, will lead us to the minimum cost. So for this particular input given, the answer will be 14. If you connect these 4 roads, the cost will be minimum. So I hope the problem is clear to every one of you. If you just notice in the problem, in the output, we are also given that it may be that the answer is not possible and you need to print impossible. In that case, let's see which is that case. Let's first of all figure out in which case we will get the answer as impossible. Let's suppose I tell you that I have nodes like this. These are the connectivities. This is the graph given to you. Let's suppose I tell you something like this. In this case, even if you repair these roads, even if you repair all the roads given, tell me, is this particular node or any node in this particular component reachable from any node in this particular component? Is it possible? No, right? So for inputs like this, where there are more than one connected components in the graph, I repeat, for inputs like this, where there are more than one connected component, in that case, your answer will be simple, impossible. And how can you check whether you have more than one connected components? Just try to think. It's very easy. You will do a simple DFS. Just do a simple DFS, and if you have to do DFS more than once, like let's suppose you start DFS from this node. This node is the first unvisited node, right? So let's suppose this is node 1 and you start DFS from this. Let's suppose this is node 2, this is node 4, this is node 5. Okay, you did DFS, you marked all of these nodes as visited. Now 1 is visited, 2 is visited. Now when you come to 3, let's suppose this node is 3. When you come to 3, you see that 3 is not visited. 3 is not visited, and you have already performed a DFS one time. In that case, this confirms that 3 belongs to a component to which 1 does not belong. This means you have more than one connected component, and in that case, your answer will be simply impossible. Because even if you are repairing all the roads, node 1 and node 3 are not reachable to each other, isn't it? Okay. So we have already figured it out, in which case answer will be impossible. If you have only one component, answer is always possible, isn't it? Okay. Now let's see how we can actually solve this. So this question is a very basic implementation of minimum spanning tree. Many of you would have heard MST, right? Minimum spanning tree. So basically, what does that mean? This means that you are given a graph. Okay, you are given a graph and you have to connect some edges. Connect some edges so that the graph that is formed after connecting the edges is a tree, and the cost is minimum. You guys can figure it out why we are talking of trees over here. Like, just imagine if I am connecting these edges. Okay, if I am connecting these edges, this is forming a tree for me, right? This is forming a basic tree for me. If I connect, what is a tree? A graph that does not contain a cycle, right? Basically, a tree is a graph that does not contain a cycle, because there is not more than one way to reach up, like to reach this particular node. It's not that you can reach from here as well and you can reach from here as well. It's not so, right? Okay, so this is the graph, this is a tree that we will form. If let's suppose I am connecting this particular edge as well, it will only increase the cost for me. It will only increase the cost for me, and that is what I don't want. So in this case, we are going to construct MST for the graph given to us. We are going to construct MST. And to form MST, there are two famous algorithms that we have. One of them is Prim's algo, and the other is Kruskal's algo. Okay. So Prim's algo involves, I will just give a bit of context. Prim's algo involves that you are selecting an unvisited node, and you are just selecting the minimum edge that goes from that node, and this is how you proceed. But in Kruskal's algorithm, what we do is we simply sort the edges in ascending order, and we keep on taking the edges until that edge does not form the cycle. So for this particular question, I am going to discuss Kruskal's algo. In other questions, if the same MST is required, I will discuss Prim's algo as well in other questions. Okay. So let me just proceed with Kruskal's algo for this particular video. So just for your information, I just wrote both of these algos, so you can just go over them if you want. For this video, I'm going to discuss the Kruskal's algo. So what does Kruskal's algo say is, sort the edges in ascending order, definitely ascending order on the basis of their weights, and then keep on taking the edge until it does not form the cycle. Okay. We will see how we will just ensure that the edges does not forming the cycle. You can simply see it via a DSU, that is disjoint set union. But let's first of all try to understand what the algorithm is. Uh, just give me a minute. Can I copy this? Okay, let me bring this down only. Okay. So let's try to understand with the help of this particular example. Okay. So if I sort the edges on the basis of ascending order, first of all, I will get the edge with weight 2, then with weight 3, then 4, then 5, then 7, then 8. Okay. So first of all, I will take the first edge, that is with weight 2, and I will connect that edge. So if you simply see, if I connect this edge, I'm not getting any cycle, right? Because currently in the graph, I only have this particular edge, 2 to 4. So I took this. Now I went to the next one. I will try to connect this edge, and you can simply see while connecting this edge, I am not forming the cycle. So I will form this weight as, I will connect this particular edge as well. Then with weight 4, it's definitely if I connect this particular edge as well, I won't be forming any cycle. So I will connect this particular edge as well. Then with weight 5, again, if I am taking edge with weight 5, again there is no cycle formed, and definitely I can take this particular edge as well. Now when I try to take this edge with weight 7, you see that I am getting this, the cycle is getting formed, right? The cycle is getting formed. So I won't take this edge 7. Similarly, when I try to take edge with weight 8, again you see the cycle will get formed, and hence I am not taking this particular edge as well, and hence the total minimum cost that you get is 14, and you are able to construct your MST. So this is the basic implementation of Kruskal's algorithm. Now how would you ensure that a cycle is not getting formed? So for that we simply use DSU. Just tell me one thing. If I am having, like, let me explain with this particular example only. While we were taking node 7, while we were taking edge with weight 7, okay, what led us to ensure that when we connect this particular edge, they will form a cycle? This is because node 1 and node 5 belonged to same component. Like when you took edge with weight 2, what you did in your DSU, you told that 2 and 4 belong to the same component. Now when you took edge with weight 3, what you told? You told 1 and 2 belong to the same component. Just a minute. 1 and 2 belong to the same component. Now since 2 and 4 belong to the same component earlier, and now 1 belongs to the component in which 2 belongs, so can I say that 1, 2 and 4 belongs to the same component? Right? Now again, when I took an edge with weight 4, I told 5 and 4 belongs to the same component. So again the 5 joins this component family. Now when I took the edge with weight 5, I told 2 and 3 belongs to the same component. So again this thing. Now when I try to take 7, I saw that 5 and 1 belonged to the same component. And if it belongs to the same component, this means now if I try to add an edge between these two nodes, it will lead me to a cycle. Because earlier 1 and 5 were already reachable to each other. And now I am connecting an edge between them. This means it will form a cycle, right? So we will simply see that when we are trying to connect two nodes, when we are trying to take an edge, we already know that edge connects which two node A and B. So we will simply see that whether A and B belongs to the same component. If yes, we won't take that edge. This is how simple the Kruskal algo works. So let's see the implementation for this and the things will be clear. So first of all, I am taking n and m as input, constructing a vector for edge weights. So basically you have weight and the two nodes that edge is connecting, and you have the edges. Okay. So took inputs of A, B and C, that is the two nodes and the weight, converted the node to zero-based indexing, and since it is a two-way road, so basically your undirected graph, so in edges of A I pushed back B and in edges of B I pushed back A. And in edge weights, I am simply pushing the weight and the two nodes that edge is connecting. Then now the first thing we will see for impossible, that can the answer be impossible? So for that, what I am doing is I am just maintaining a visited vector, initializing the components to 0, the total number of components you have, and trying to do a DFS from every node that is not visited. So if the node is not visited, I am increasing the components and doing a DFS. So this is a simple DFS I am doing, where I am marking the node as visited and going over all the child, and if the child is not visited, doing a DFS from that child. This is simple DFS that I am doing. Now, if the number of components is greater than 1, so every time when I am trying to do a DFS, I am increasing the component, because every time from a new node when I do a DFS, this means it belongs to a different component. So I am increasing the component number, and if the component number exceeds 1, this means that even if I repair all the roads, I won't be able to make every node reachable to every other node. So in that case, I am simply printing impossible and returning. Otherwise, I am just applying a simple Kruskal's algo, where I am first of all shorting the edge weights vector that I had. So since the first member of this is the weight, so it will get shorted on the basis of weight. And I am constructing a object of union find struct that I already have. So I am not going to discuss this union find, how it works. Basically DSU, how it works. You can simply look up for any code if you don't know. First, try to understand how DSU works and all, and then you will be able to understand this problem very well. So I'm constructing an object of DSU and initializing the size to n. You can simply see I have this constructor with me, where I am saying the size, or basically the number of nodes. Then going over all the edge weights, the distance and nodes I am just initializing with edge weights of I, and U and V are the two nodes that are getting connected by this particular weight. Okay, so basically if you just look to the structure of edge weights that I have, this is a pair of pair. So the first member is actually the distance, and the second member is actually the pair of nodes. So I am just taking it or destructuring it to two nodes U and V. Now, if the leader of U and leader of V are same, if they are not same, I am simply merging this and adding the weight, that is the weightage, edge weight to my answer. If the leader was same, what does it mean? It implies that the two nodes U and V belong to the same component, and in that case, I am not adding that edge weight to my answer. So if the leaders are not same, adding my edge weight to my answer and also merging these two nodes U and V. So now U and V will belong to the same component. At the end of this, I am simply printing out this answer, and I am pretty much sure that this answer will be the minimum one, such that every node is connected to every other node. So this was a basic implementation of Kruskal's algorithm. I hope all of you understood it. Thank you.